Karni, and this is my topic for the short story assignment submission. So I've taken the paper PROPEX-RAG, Enhanced GraphRAG using prompt-driven prompt execution. So the authors are from IIT Gandhinagar in Gujarat, and then this paper was published in like around November 2025. And then I'll also be attaching the RXIV file below in the description if you want to go through it. So my work is solely based on what they have concluded, and I'm just like explaining what it is like, uh, the architecture, what results that they get, and what are the practical takeaways. So let me begin by saying that the core recipe is like symbolic graph plus prompt policies plus a short personalized PageRank traversal. This combination helps us pull the right evidence early, keep the retrieval controllable, and produce like stable cited answers. So basically, in this presentation, I'm going to focus on the architecture, the design choices that have actually moved the needle, and also the results on the standard multi-hop benchmarks. So the next slide that I want to go through is why multi-hop RAG needs graphs plus prompts. So dense retrievers that are already there shine when one paragraph holds the answer, but multi-hop questions, like, they split the evidence across documents. So when the relationships matter, like who bought whom, or who inspired which book, or like what happened before what, when there's like a story that is going on, or like there's a link between something that happened and something that is going to happen, pure embeddings can blur those kind of links. So that is why we have graphs. Graphs like expose entity level structure, and also prompts which steer traversal and filtering. So graphs basically bring back the entities and relations explicitly, and the prompts that we have give us policy level control over what to keep and how to search. So our goal or our targets are interpretability, high recall at small k value, and also steady final accuracy. So the key idea in PROPEX-RAG. So basically, offline we build an entity-centric symbolic knowledge graph, which has entities, fact triplets, and cautious synonym or context edges. And then online, which is nothing but at the query time, we use a prompt gated filter to keep only the triples that matter to the question, and then we convert these into those seed entities. And then after that, we run a short personalized page rank from those seeds to focus on the most relevant neighborhood, and then re-rank these passages using symbolic overlap with entities and facts. So, thus, we can say that the generator receives a curated evidence first bundle instead of like a random pile of similar paragraphs. So, this is the architecture overview. This is something that I generated using GPT. So, if you see, we have two sides, there's like the indexing side, retrieval side, and then the final whatever answer generation. So, on the indexing side, we extract entities and fact triplets, detect synonyms with embeddings, and assemble the symbolic graph with typed edges. And on the online retrieval side, a question that is there becomes a small set of k top facts, and top k facts, and then we prompt filter them, derive seed entities that we've already discussed, and run the ranking algorithm. And then after that, the last step is to like collect the ranked passages for generation. So the legend that we have, it clarifies node types, edge types, and where PROPEX policies act, specifically at the filter and the seed steps. The separation of concerns is important here, like what governs what or what has what. So we can say that the prompts that are there govern the behavior, the graph structures have knowledge, and then the PPR searches efficiently. So this is something that I generated, and then this is something that was already there in the research paper that we have used. So if you see, this is more clear. The top band is like basically indexing, and then the bottom band is retrieval. same as before, but this is easier to understand. So the first thing is like the offline indexing, where we have the passages, and then that in turn gets converted into entities and facts, and then we have a similarity matrix that is generated, and then after that the final thing is like the symbolic knowledge graph. So if you see, these are like these steps here, and then after that this is the retrieval side where the query is sent, and then from the embedded seed entities we get the top k similar facts, and then we combine both the filtered facts and the seed entities, and then based on the entity guided graph traversal we get the ranked passages, and in this we take the top k passages and then combine with the earlier fact overlap, and then the final answer generation. So in this we have three steps: prompt driven information extractor, synonym detection by embedding, similarity augmented graph encoding, and then in the phase 2, which is nothing but the on-rail retrieval, we have embed question via embedding model, entity seed scoring, top k facts that are there using cosine similarity, and then top passages are retrieved, and then oh, sorry. Yeah, the first step is this. The second step is top K, and then filter relevant facts. And then after that, the entity seed scoring is done, and then top passages are retrieved, and then we re rank them, and the final answer is sent out. So, this is the end to end walkthrough. So, let's say we start with our top K fact triplets from the corpus. The filter prompt like keeps only the ones that truly bridge the question, which are like mapping. From those kept triplets, we extract the seed entities and run a short PPR on the typed graph to surface the tight neighborhood. And then after that, when we like the top passages are picked, and then fed them into like we feed them into LLM, and then we return a cited answer. So this is the end-to-end walkthrough we can like go through. So we have the user question, and then we get the triplets, we get the prompt, filter triplets, seed entries, and then this is where the ranking happens, and then this is where the final answer is sent. If you want, we can like this is an example that I have here. Moving on, this is like the pipeline. I would say the first thing is index, which is the offline thing that happens. Retrieval is the online step, and the last part is the generation. So the first in the indexing, we do extraction of entities plus fact triplets, add synonym or context edges, and then store sparse entity passage links, and then inverse passage frequency. This is what happens on the online side where the query is sent. So top cave triplets using the prompt filter, derive seed entities, and then run the PPR algorithm, and then re-rank. And then this is the final thing where the fact overlap, everything is done, and the final answer is generated. So these are a few results that were there in the paper. So on 2 wiki multi-hop QA, PROPEX-RAG delivers a strong F1 compared to like the competitive baselines, as you can see. And then all the systems were evaluated under a consistent deterministic setup with top 5 triplets after the filter and short PPR pass. The reason this matters is that early correct evidence reduces variance downstream in generation. And then we'll see a similar data set, similar pattern in the next data set that we have. So this is the hotpot QA, and here also we again see a solid F1 and consistent performance relative to strong methods. Same evaluation recipe like prompt filter, facts, seeded PPR, symbolic re-ranking. And then the key lesson that is here is that controlling retrieval, like not just scoring, leads to a stable answer quality. So these are the results at a glance. So so the summary pairs answer quality with recall at 5 for our proxy our proxy for early evidence. The headline is simple, like a high recall at 5 means that the system usually retrieves the right evidence within the first few items. So that is why the generator can be deterministic and still achieve strong metrics. In practice, this translates to few retries, fewer hallucinations, and easier debugging. So if you see, these are like good F1 scores at whatever recall that we have mentioned. Moving on, what moves the needle is that the entity seeded PPR concentrates probability mass on the relevant subgraphs, which means that it boosts the early evidence. Second, prompt gated fact filtering removes loosely related triples before traversal, So this improves both the both the precision and F1 and reduces the noise. And then the third thing is the symbolic overlap pre-ranking prioritizes passages that explicitly name the entities and facts, which improves grounding at smaller k. Everything else is like basically secondary. After that, we have a few error modes and the mitigations that we can do for them. So for alias or correference confusion, we can mitigate it using a light coref pass, etc. And then noisy synonym edges can be mitigated by using this. And then over including fact set, we can reduce the top k facts. And then under seeding, we can allow tie break fallbacks. And then passage re-rank misses, we can increase the entity fact overlap weight. And then if we have a stale graph, we can schedule incremental rebuilds or like flag new aliases via vlogs. So I'm also gonna put this slideshow on SlideShareNet if anyone wants to like go through it there. And then we have a few reasons why we should use PROPEX-RAG and when it is not to be used. So you basically use PROPEX-RAG when questions require two or more hops, when stakeholders want traceability between them, or when your domain has evolving terms analysis. And then it is less ideal, I would say, for single hop factoids or like very open web long context tracks where the graph maintenance can be kind of difficult, or if it's like an opinion or vague kind of question, then that is also when not used. And then the rule of thumb here is that if you need auditability or to to bridging evidence, this approach is like strong. And then after that, we have a few practical trips where it says keeps prompts short and auditable, and then cache offline graph, keep traversal parameters simple, log per query seeds paths and passages during to debug and tune. We also have a few limitations and future work that can be done according to the authors and also according to my personal opinion. So the graph maintenance for changing corpora, synonym drift, and then also scaling to huge graphs, partitioning, locality aware PPR, and then exploring hybrid learned re-rankers under cost constraints. And then these are a few takeaways. So the I would like to like I have a few points here, but I would like to uh, combine them and talk about them in like three major points. First thing is early evidence leads to stable answers. That is the main driver behind all of the results. Second thing is structure plus control like beats brute force for multi-hop, like basically a symbolic hop, prompt policies, and a short PPR traversal. And then third, the system is training free on retrieval, interpretable, and reproducible, which makes it practical to operate and evolve. And then I want to acknowledge the original authors of the paper. So Tejas, Manan, and Ravi Hegde, who are all from IIT Gandhinagar. So huge thanks to them for coming up with this research paper and allowing us to like uh, understand it in such a better way that we are able to like derive something out of it now. Yeah, thank you. So yeah, if there's any questions, maybe I can like take them in the comment section. But yeah, I do have a Medium article on the same paper which I will be posting in the description. So yeah, thank you.